We will begin our introduction to aerodynamics AE 6015 with some basic equations. We're going to start with 2D, then later on generalize it to 3D. So it's easier to think in terms of 2D, draw things in 2 dimensions. So that's how we will proceed and continue from there. So one of the first concepts that we need to become familiar with is called a concept called Knudsen number. Knudsen number is a non-dimensional quantity. It's a ratio of a quantity called lambda, which is the mean free path, divided by the vehicle dimension, such as a chord of an aerofoil, or a span of a wing, or a length of the fuselage, whatever you think of as a characteristic length of the vehicle. What do we mean by mean free path? It's basically air is made of molecules. You have hydrogen, nitrogen, oxygen, hydrogen, you name it. And they are discrete molecules, so they are constantly moving about and they are colliding with each other. So the average distance that a molecule travels before it bumps into its neighbor is called a mean free path. For example, in a classroom, you may be sitting next to a neighbor, so the mean free path may be like a 1 foot or so. If you're on an airplane, again, it's going to be 1 foot, perhaps less on a highly crowded seats in an airplane. So molecules are very closely spaced. They are micrometers apart. So normally at low altitudes, lambda is of the order of micrometers, L is of the order of meters. So Knudsen number is very, very small. On the other hand, at high altitudes, especially in the outer edges of the atmosphere, where there are very few molecules, they are far apart. So, for example, if you think of a space shuttle that is re-entering atmosphere, or the International Space Station, the vehicle length is tens of meters long. The mean molecular path is also several meters long. So lambda over L is no longer a small number. Knudsen number is large. So if the Knudsen number is small, the molecules are close to each other, then we can start talking about average properties such as velocity, density, pressure, temperature, and so forth. We are going to discuss these in this lecture. Let's think of velocity first. Think of a start of a Peachtree road race where people are crowded with each other. When the bell rings, or in that case when the flag drops, you start running, but you can't run very fast. If you run faster than your neighbor, you're going to bump into them. If you run slower than your neighbor, somebody from behind you is going to bump into you. So the whole crowd is traveling at almost a uniform speed because of this collision that averages out the velocities. Therefore, you do not have an extremely fast-moving fluid particle, extremely slow-moving fluid particle. Therefore, you have some average velocity. So you can then take thousands of molecules, take an average of properties, and treat as though all these particles are one continuum, one lump of mass that is moving as though it's a solid piece, even though it's made of discrete molecules. So we call this the concept of continuum. So under the concept of continuum, we have several properties that we have to worry about. We have the organized motion about the 3 axes, x-axis, y-axis, and z-axis, which are u, v, and w. Depending on the coordinate system, x may be one way, y may be the other way. We have to pick it based on our 2D flow or 3D flow. We will discuss those things later. But all we need to know is there are 3 coordinate directions, therefore 3 organized motions of the velocity. This could be either a free stream in a wind tunnel coming towards an airplane, which is stationary, or in an airplane coordinate system, you're flying, but in the airplane you're thinking, I am stationary, the molecules are coming towards me. Then u, v, w are the 3 Cartesian components of velocity. So we are applying the concept of continuum. That means we are not dealing with discrete molecules. We are dealing with a collection of molecules, a group of molecules, averaged properties. How about density? Density is mass per unit volume. Therefore, the density will have the units of kilogram per cubic meters or slugs per cubic feet. Slug is related to pound mass, by 32.2. So if you weigh yourself in a machine, let's say this morning, let's say you are 160 pounds. It's really 160 pound force. Your mass is 5 slugs. 5 slugs times G equal to the force. Okay. So one slug is 1 over G times the pound mass. So mass unit in British unit system is slugs. Therefore, the density is slugs per cubic feet. How about the pressure? Pressure would be newtons per meter squared. This is the force exerted by the molecules normal to an area per unit area. So if you think of a 1 meter square stamp, all the molecules, when it collide with each other, all the molecules, neighborhood molecules at that boundary, these molecules exert a force on each other, so that normal force, normal to the surface per unit area, is what we call pressure. So it will have a units of Newton over meter squared or pound force over square feet. Distance is always feet, area is square feet, force is pound force in the British system. In the international system of units, Newton is the force, meter squared is the area. By the way, 1 Newton is 1 kilogram times 1 meter per second squared, F equal to MA. Then comes temperature. Temperature is a measure of the random molecular motion. Up to now, we have been talking about the organized motion U, V, and W. This is the average velocities. On top of it, you have a random motion of the molecules. For example, if you look at a Braves game, the start of the game, most of the people are coming in, but some people will be going out to get maybe a drink or something through the gate. So there's a milling about motion, so random motion, left to right, front and back in 2D. In 3D, it's a left to right, front and back, up and down. So this random motion of the molecules, which is, when you average it out, you get the orderly motion, but the random motion has got some energy associated with it. Also, the molecules are diatomic for the most part. Therefore, they have 3 axes. 2 of the 3 axes have a large moment of inertia. Think of a dumbbell. Dumbbell has got 2 masses connected by a rod. So nitrogen is 2 nitrogen atoms connected by an invisible bond. So that's a dumbbell. So when you dumbbell rotate it about 1 axis, it's going to produce a large moment of inertia. It's like a ballerina spinning in the horizontal plane. Okay, so there's got a moment of inertia associated with it. There's also an energy associated with it. 1/2 times moment of inertia times angular velocity squared is the energy. If you have somebody tumbling like a somersault, then they are rotating in the other direction. So if you think of as a dumbbell spinning in the other direction, then it's also going to have energy in it. But if a dumbbell is spinning about its own axis, it does not have not much energy, because the center of gravity is on the axis of the dumbbell. So only 2 of the 3 axes are important for rotational motion. So there are 5 degrees of freedom, or 5 ways energy is expressed. 3 random motion, linearly left to right, front to back, up and down, and 2 rotation. Therefore, we have a total of 5 degrees of freedom. The energy associated with it is called the internal energy. Internal energy per unit mass is called the specific internal energy. Temperature is a measure of the specific internal energy. It's in degree Kelvin in the international system of units, or degree Rankine in the British system of units. Now, P, rho, and T are not independent of each other. For ideal gases, thermally perfect, calorically perfect gases, we could write P as rho times R over T, where R is called the gas constant, T is temperature, rho and T we have defined it, P we have already defined. This gas constant is a universal gas constant divided by the molecular weight. Since air is a mixture, The molecular weight will be the molecular weight of the mixture based on what percentage is nitrogen, what percentage is oxygen, what percentage is other gases, and so forth. So you kind of weight it based on the percentage of various gases by mass that is present. Therefore, we have 6 equations, properties, rho, P, T, U, V, and W. Therefore, we need 6 equations. We already have one equation here, equation of state. Therefore, we need 5 more equations. These are equations of conservation of mass, that is 1. Conservation of momentum, U, V, W, that's a 3 momentum, 1 plus 3, 4. Then conservation of energy, which is the 5th PDE. So we will get 5 integral equations or 5 partial differential equations, plus this extra equation of state, or the 6 equations we have to solve for these 6 properties. So now we are going to talk about streamlines. Streamlines are lines in space drawn so that at every point on it, the velocity is tangential to this line. In the next lecture, we are going to mathematically define it and come up with a mathematical equation for it. But right now, we think of it as a line in space at every point on it. If you draw a tangent to it, the velocity is along this. That means there's no velocity normal to the streamline. If you have a bundle of streamlines forming a tube-like shape, then it's called a stream tube. So that's shown in here. So you have a bundle of streamlines. They form a tube-like structure. This is the cross-section of the tube here. This is the cross-section of the same tube here. So the cross-section may be changing because the streamlines are coming together towards each other or departing from each other. The important thing is mass can enter and leave across this green boundary, but mass cannot leave or enter normal to the streamline because by definition, the velocity has to be tangent to the streamline. Okay. So I'm going to lower the sound of my microphone so that it gets some sound effects. To reduce it, I'm going to reduce it and resume where we are left off. All right. Now, this is the stream tube. So within the stream tube, mass cannot be created or destroyed. So that's what the conservation of mass implies. So whatever mass is coming through the left side either has to leave through the right side, otherwise the mass will continue to increase. Like if you blow air into the balloon, air is coming in but nothing is going out, then the balloon will keep on expanding. Okay, happens to me on pizza night. I keep consuming more and more, so the mass is steadily increasing. So the rate of change of mass in a steady flow, then whatever enters to the left side must leave to the right side. Okay, so if you have 1 kilogram per second entering from the left side, it better leave 1 kilogram per second on the right side. So how do we express in mathematical form? So this is the stream tube. Left side has got an area of A. In a compressible flow, density may change, the velocity may change. Remember, now we are talking about the velocity along the streamline. There's no normal to the streamline. So this is almost like a scalar. V1 is a scalar. It is normal to the blue boundary on the left side. On the right side, area has changed, density has changed, volume has changed. Therefore, the mass flow rate has changed. If you look at the units, density is kilogram per meter cubed, area is meter squared, velocity is meter per second. So when you multiply all the three, the mass flow rate is kilogram per second coming in. In a steady flow, the same amount must leave to the right boundary. Therefore, mass cannot be removed, destroyed. So rho times A times V is a constant. In an incompressible flow, rho is a constant. Therefore, volume rate of flow is a constant. Cubic meter per second is a constant. That's the mass flow rate, very, very simple conservation of mass along a stream tube. That's one of the 5 equations we need. Now we are going to develop a momentum equation. Unfortunately, since everything is tangent to the streamline, nothing is perpendicular streamline, we are able to develop a momentum equation for now only along the stream direction. So this is a slice of that stream tube. The left side is, we are going to apply the momentum equation based on the Newton's second law, which says rate of change of momentum of particles is the forces acting on it. So what are the particles we are talking about? We have particles coming in from the left side, particles leaving to the outside. Let's say particles come in from the left side with one momentum. They leave through the other momentum. If something has changed, this change must have been caused by forces either on the boundaries or in the interior. So this is F equal to ma. So that's what we're going to apply. Okay. So again, we look at the left side and what happens on the right side. Okay. Then we are going to look at the change in the momentum. So the area is density, velocity, area. On the right side, you have density has changed, velocity has changed, the area has changed, but by a tiny amount, infinitesimally small amount. Okay. Therefore, the rate at which the mass is coming in is rho VA, but the same mass is going to the right side because mass is conserved. This is a steady flow, equal to rho plus delta rho times V plus delta V times A plus delta A. That's the conservation of mass. How about the momentum rate? Rate at which momentum is coming in is the mass flow rate times the velocity. So it's rho times V squared times A. That's what's coming in. What's going out? Same mass flow rate, which is rho VA, but now it's leaving with a different velocity, higher or lower, we don't know. All we know is V plus delta V. The delta V could be positive or negative. But we do know that the rate of change of momentum is what comes in minus what goes out. So the rate of change of momentum is momentum out minus momentum in equal to rho VA times delta V. Mass flow rate times the change in the velocity. Mass flow rate has not changed from left to right. So the mass flow rate remains the same, but the velocity has changed. So what causes this change? It must have been caused by the forces acting on the control volume. Control volume is this red slice of the stream tube. So all the molecules inside the molecules have experienced some forces. These forces can be pressure forces normal to the wall, viscous forces normal and tangent to the side of all the walls. When I say wall, I'm talking about the left boundary, right boundary, but also all the lateral boundaries, the slanted surface. Then you can have body forces such as gravity, electrical forces, magnetic forces. For example, if you have a flow of ions, by using a magnet, you can accelerate or decelerate, ions or iron particles, for example. You can use the electrodes to accelerate or decelerate charged particles. So those are all body forces: gravity, electricity, magnetism. We are going to neglect them for the time being. We are not used in our course. We are also not using viscous forces for the most part in this course. So the only forces we have to worry about is the pressure forces. So this rate of change of momentum is caused by the forces acting on the stream tube. The forces are body forces plus pressure forces plus viscous forces. We're only going to worry about pressure forces, not about viscous forces, not about the body forces. So let's look at the left side. The force is pressure times area. Pressure is Newton over meter squared. Area is in meter squared. So this is increasing the momentum. So this is the positive change to the rate of change of momentum. How about on the right-hand side? The pressure has changed. The area has changed. This force is acting in the opposite direction. So this is decreasing the momentum. It's a headwind type of a force. So it's slowing you down. It's like a linebacker running into a running back, slowing him down. But we should not forget the lateral boundaries. Lateral boundary, we need to know the area, but also we need to know which way are the forces acting. Left side, right side, top, bottom, because it's the slanted surface. So what we do is we project these areas to a horizontal rays because we are mainly interested in momentum in the horizontal direction. So we project it along the x-axis. This is the A plus delta A, which is the right side boundary. Project the left side boundary, then the difference is delta A. This is the donut-like shape. This is the projected area. So this is the area on which the forces are acting on the lateral boundary. By lateral boundary, we are talking about the slanted surface of this red control volume. So these forces have got a vertical component, which we don't care about, but we are interested in the horizontal component. So which pressure should I use? Should I use the P or P plus delta P? When in doubt, use the average value, P plus half of delta P, times the projected area, which is delta A, that's a horizontal force. So we use all the forces from left to right, then we use all the forces from right to left. The difference is the net force. This is what is causing the net rate of change of momentum. So net force is all the forces from left to right, which is P times A, which is acting on the left side boundary. The second term is on the slanted surfaces. The last term is on the right side boundary. Neglecting the second order product term, delta P times delta A, we get roughly minus of A times delta P. This is the force. So F equal to MA. So rate of change of momentum equal to the force. The area A drops out. Therefore, we get rho V dV plus dP equal to 0. So we have to remember the assumptions we made. It's a steady flow. So we are not talking about a balloon-like thing where momentum can increase inside the control volume. Control volume keeps changing its shape. It's a fixed control volume. Steady flow. Inviscid, no viscosity, no body forces, no gravity, electrical forces, magnetic forces. For example, if we inside a control volume, if we have a propeller, it may be accelerating the flow. If we have a little wind turbine, it may be decelerating the flow by removing the energy. So those are also distributed body forces. Compressor, turbine, none of them are present in our control volume. Here no body is present, no rotating, moving body. So this is where we use, usually when such things are not present. So this is the momentum equation. This was developed by Euler. Therefore, this is called the Euler equation. If density is constant, we can integrate it. Then you get a Bernoulli equation. Sorry for the typo. It should be EQU. I will try to fix it in a later version next year. So Bernoulli equation is 1/2 of rho V squared plus P equal to constant. So the assumptions are steady, incompressible, inviscid, no body forces. So let me go ahead and fix it while I'm here. So this is the Bernoulli equation, EQ, U. All right. So that's the Bernoulli equation. So in incompressible flow, low speed flow, which is the first few weeks of our lecture, we will use Bernoulli equation. By the way, what is this constant called? Sometimes we use the word P naught, which is a stagnation pressure or total pressure. Hydraulics people will say stagnation head or total head because they are used to thinking of a column of water, head, type of a thing. But we will use a stagnation pressure, P naught. Okay. P naught is the pressure the molecules will have. It is completely brought to rest. Then all the velocity, all the kinetic energy, which is 1/2 rho V squared, is converted into pressure energy. Okay. How about energy equation? So we are going to develop a general equation for compressible flow. If you're only worried about incompressible flow, we can just use this bottom equation, 1/2 rho V squared plus P equal to constant. How about the energy equation for a compressible flow? Again, we are thinking of a stream tube, a collection of particles, same group of particles. Therefore, a group of particles of fixed identity that's entering the control volume and leaving the control volume is called a system. Okay. So, first law of thermodynamics says that the change in the internal energy, remember, internal energy is caused by the random motion of the molecules, but also organized motion of the molecules may be present. Okay. Random motion is 3 random motion in the XYZ direction and a 2 rotational motion like a ballerina or a dumbbell about 2 of the 3 axes. In reality, there are 3 axes, but one of them has got a very low moment of inertia. A dumbbell along its main axis has got a 0 moment of inertia because the center of mass is right on the axis. But about the other 2 axes, it's got lots of moment of inertia, therefore lots of energy. Okay. So this is the energy. Thermodynamics says the energy can be changed by either adding heat or you're doing work. Okay. So this is the first law of thermodynamics. Okay. So you have an organized motion, u squared plus v squared plus w squared, just like in the Bernoulli equation, which is this 1/2 rho v squared that we saw earlier. But you have now the random motion of the molecules, internal energy we have to contend with. We have to worry about adding of the heat and adding of the work. Now, in our problems, we are going to extend this law to our control volume. So when we talk about energy, we need to talk about the kinetic energy plus the internal energy. Internal energy is the random motion part of it. Kinetic energy is the organized motion part of it. So again, in a ball game, people seem to be organizedly coming from left to right, but if you look closely, you will see some milling motion. If you look at a cloud, most of the cloud will be moving from one direction to the other direction. But if you take a binocular and look at it carefully, you will see random motion within it. So you have an organized motion kinetic energy, random motion kinetic energy. So we need to, when you talk about delta U, we have to worry about both components. We are going to neglect viscous forces as before. We are going to assume steady flow, so nothing is changing with time. And we are going to assume that there are no heat addition by conduction, diffusion, or chemical reaction. Therefore, this Q term is going to disappear. So when you don't have any heat addition, we have something called an adiabatic flow. A process is anything that changes the properties of the fluid, such as change in the density, pressure, or temperature. A process in which you don't have any heat addition or heat removal is called an adiabatic process. So we're going to set Q, or the heat added or heat removed, to 0. So we are talking about adiabatic, inviscid, steady flow. So this is our control volume. We're going to apply the first law of motion, first law of thermodynamics to this system. Mass is conserved. Therefore, density times velocity times area is conserved. Pressure work is pressure force times velocity, P1A1 times V1. On the right-hand side, energy per unit mass is internal energy, which is specific heat, CV, times T from thermodynamics. That's per unit mass, plus 1/2 of velocity squared, again per unit mass. 1/2 mv squared in the classical dynamics is the kinetic energy of a projectile. But m is mass, so if you remove the mass, you get 1/2 of kinetic energy, okay, with just the velocity squared. That's per unit mass. Okay. So you'll take the mass flow rate and multiply by energy per unit mass. That's how much is the energy that is flowing in. Then you'll take the same mass flow rate times how much of energy is flowing out. That'll be the energy flowing out. So the energy flowing in minus energy flowing out must have been caused by the forces acting on the system. The only forces we have to worry about is pressure forces on the left boundary and on the right boundary. We don't have to worry about lateral boundary because there's no velocity perpendicular to the lateral boundary because streamline cannot cross the control volume. It can enter the control volume from the left it can leave the control volume from the right. Therefore, the energy flowing in, we have to worry only about from the left boundary and the right boundary. Rho 1 A1 V1 is same as rho 2 A2 V2 because the mass is conserved. So energy out minus energy in, the change in energy must have been caused by the pressure work on the left boundary, left face, minus the pressure work on the right face. On the right face, it's negative because the force is acting one way towards the control volume, velocity is in the opposite direction. So when you do a dot product, you're going to get a force dot velocity, you're going to get a negative number. That's why it's negative of P2 minus A2. And there's no heat addition. Therefore, the first law of thermodynamics becomes rate of change of energy flow minus in minus out. The first term on the left side is energy flowing in, energy flowing out. Inside the square bracket, we have the random kinetic energy and organized kinetic energy, equal to the pressure work on the left boundary minus pressure work on the right boundary. The reason we have negative direction is force dot V is negative on the right side face. Now we can divide through by rho 1 A1 V1. This is same as rho 2 A2 V2. Therefore, rho 1 A1 V1 and rho 2 A2 V2 will cancel from the left side. On the right hand side, you'll get P2 over rho 2 minus P1 over rho 1. So take P1 over rho 1 to the left side, keep P2 over rho 2 on the right hand side, bring group 1 terms to one side, subscript 2 terms to the other side, then you get a nice algebraic equation. Now P over rho is RT, therefore P1 over rho 1 is R times T1. P2 over rho 2 is R times T2. So this is the conservation of energy. Okay. Now R is a CV, which is a specific heat at constant volume, plus gas constant R, equal to Cp, which is a specific heat at constant temperature. So Cp times T plus V squared over 2 is a constant within a stream tube. Therefore, if you shrink a stream tube to a tiny, thin streamline, then this quantity is constant along a streamline. In thermodynamics, we call the quantity Cv times T, specific internal energy. Cp times T, we call it specific enthalpy. Cp times T plus V squared over 2 is called as total enthalpy or a stagnation enthalpy, H naught. So H plus V squared, which is equal to H naught, is a constant along a streamline. So sometimes we write H naught as Cp times T naught, where T naught is called a total temperature or a stagnation temperature. Now if you recall, Cp over Cv is gamma, Cp equal to Cv plus R. So you could group it so that Cp equal to gamma R over gamma minus 1. Gamma RT is the speed of sound squared. Velocity over speed of sound is Mach number. So using all of these things, you can get an expression for the stagnation temperature. In an inviscid flow, in the absence of viscosity, in the absence of body forces, in an adiabatic flow, stagnation temperature remains constant, even across a shock wave. So this is what is the first law of thermodynamics gives for a compressible flow as an energy equation. So in compressible flow, we use Bernoulli equation. In compressible flow, we will use this equation. How about the second law of thermodynamics? Okay. This is the summary. Conservation of mass for a stream tube, conservation of momentum, conservation of energy, and the assumptions are steady flow, inviscid flow, adiabatic flow, no body forces. As I mentioned earlier, if you have no heat addition, it's called an adiabatic flow. If the process is reversible, that means you can bring the system, that means our particles, and the surroundings, which is the environment, back to its original state. This is what happens when an airplane is flying in subsonic flow. A molecule starts at one pressure, velocity, density, outside the boundary layer I'm talking about. It flows past the airfoil. Density, pressure, velocity, everything changes because of the disturbances caused by the airfoil. But by the time the molecule reaches the downstream boundary, it has gone back to its original state. When it happens, you have a reversible process. That means you have returned the system back to its original place, and you have everything back to normal. Humpty Dumpty has been put together back again at the far downstream boundary. But what happens if we have a shock wave? When the molecule crosses the shock wave, it goes through an irreversible change. Entropy rises. Stagnation temperature remains the constant, as we saw earlier. But the entropy, because the entropy goes up, some of the other properties, such as the stagnation pressure, decreases. So properties cannot be put back into its original state. Then you have an irreversible process. Flow through a shock wave is a prime example of an irreversible process. Boundary layer flows, anything that is viscous is an irreversible process. If you have a heat addition, then in an adiabatic process, you have a change in the specific entropy. Specific means per unit mass. Entropy per unit mass is always greater than the amount of heat you put in, small amount of heat you put in calories or in joules, divided by temperature unit, whether it's a degree Kelvin or Rankine appropriate units. Always it's either equal or greater than. Equal is if it's a reversibly added heat or removed, greater than if it's irreversibly added or removed. What happens if you have an adiabatic process? Delta Q is go to 0. Therefore, in a reversible adiabatic process, ds is 0. Therefore, S is a constant. In a reversible adiabatic process, so-called an isentropic process, entropy is constant. Then you have, in addition to the equation of state, in addition to the temperature ratio relationship, we saw T naught relation to T, we can also bring into play other equations such as P is proportional to rho power gamma. Then we can bring a relationship for density, temperature, pressure, a lot more algebraic equations we can play with. Okay. So this is the module that deals with properties of gases, how we can develop equations along a stream tube. Then we talks about how to conserve the mass within a stream tube, how to conserve a momentum within a stream tube, what happens, and what happens with the energy, okay, in the compressible sense and also on the incompressible sense. So we are completing this module at this point, and you'll be able to find this video in the lecture and then immediately below the lecture in your module.